So I'm an engineer on the Cultural Institute, and you should have been on a tour of the Cultural Institute earlier today, so probably know a bit about it, but basically we're a team of engineers whose mission is to democratize access to culture. And one of the ways we do that is by helping museums digitize their collections. So that's why we built the art camera, which is this thing right here. And it's a camera to digitize paintings in very high resolution and also efficiently at low cost. So it works by taking automatically hundreds of very zoomed in pictures of an artwork, and then we stitch all these pictures together to make a single very high resolution image. We call these images gigapixels because they typically contain a few billion pixels. So that's one example. That's one of the first paintings we digitized with the art camera. It's by a street artist called Inti. And if you zoom in, here is the kind of resolution that we can get. So here you can see details that you would not be able to see with your naked eye. So we actually get better than eye resolution. And if you were to display this at 100 pixels per inch, which is a typical display resolution, then it would be about 10 by 15 meters. So that's the kind of thing we can get with the art camera. And now let me tell you a bit about what it's like for me working on this project. So I joined this project about 10 months ago, and when I first joined, it was a bit like the first time I saw this. I was like, what is this? It's a big project with lots of moving parts. There's three main components. The first component is the camera itself, the hardware. So the actual DSLR camera is an off-the-shelf Canon camera, but it's in a custom enclosure, and there's also inside a custom circuit board with the custom firmware. Then the camera is controlled by software running on a laptop that's connected via USB. So on that laptop, there's 8 different servers running to control the camera and also show a web UI for the operator. And the third part is the stitching pipeline, so the software to actually piece all the pictures together to create a single image. And that doesn't run on the laptop, that runs in Google data centers. And the pipeline looks like this. So I was like, what? And all of this is written using, there's some C, there's lots of C++, quite a lot of Python, there's a bit of Java, there's HTML and JavaScript and CSS, of course. So it's lots of moving pieces. And what's also fun about this project is that we're just 2 software engineers working on it. So that means we all get to work on everything. Also, so my colleague joined the project 12 months ago, and I joined 10 months ago, and it's just been the 2 of us since. And that means that we don't have anybody to ask questions to, and we don't know how things work or why they work that way, or is there really a good reason for that, because sometimes there isn't. And so it's always a bit of a detective story when we try to investigate issues. Another fun part of the project is working with hardware. So that's me working with hardware. One of the things when you work with hardware is that you can't just write unit tests, for your software. So at some point, you really do have to test with the actual camera by plugging these things physically. We do have unit tests and integration tests that use a fake software camera. But recently, for instance, I wrote a bug, and that went into production, and we didn't notice because the bug was only happening on the real camera, not on the fake one, because we discovered that there was a difference between the fake camera and the real one, and we were not aware of that difference. So these things happen. That's why you have to test with the camera, and even with several cameras and in different situations. Another fun part with hardware is that these cameras get sent all over the world to museums, and sometimes things get wrong at the museum, and then we have to try and debug remotely. So recently I had to SSH into an art camera laptop in Colombia to try and help with the capture that wasn't going well, and the connection kept dropping. So that was also lots of fun. But now, so I understand this project a bit better, so I can run you through how capture happens, how we get to this gigapixel. So this is the basic flow. First, we ship the camera to the museum. Then we set it up for each painting. Then we capture the painting. We upload the data to Google data centers where we stitch everything. And then we're ready to publish it on the web. Each step in a bit more detail. So first, we center the camera on the painting. And at this step, we also decide what distance to put the camera from the painting. There's a trade-off because so the closer the camera is to the artwork, the more pixels we get, the better resolution, but also the more time it takes because it means we need to take more picture. And actually, you should be able to see here, to help with the distance, we have a sonar here that tells us the distance to the painting live. The second step is capturing the color checker. So that's a really important step. The color checker is this object that you see on the left. It's a piece of plastic with patches of color that have very precise, predefined colors. And taking a picture of this object allows us to record what the lighting in the room was like when we captured the painting. So that's really important because when you take a picture with the camera, the RGB values of the pixels depend not only on the object that you photographed, but also on the lighting. And so taking a picture of this and recording the lighting allows us afterwards to apply a correction algorithm to the colors of the picture to make it look like all the artworks were captured under the same lighting conditions, even though that's not necessarily true. Third step is the actual capture. So the camera stays fixed, but it can rotate left and right and up and down with this, which is called a gimbal, and there's two motors. And so it automatically takes, as I said, hundreds of pictures. This shows you the pictures that we would take for an artwork that's about 1 meter wide at 2 meters distance. So that's roughly 1,000 pictures, and it would take about an hour. Once we have all this data, we upload it, and then we put it in the stitching pipeline. So I showed the diagram of the pipeline earlier. It's kind of complicated. But the basic idea is that we first look for features in all the images. So features are like points of interest on the images, things that we can describe, like edges or corners. And they're represented by squares on this slide. And then we try to match features between neighboring images. So like if we find this corner in an image and we find the same corner in another image, we say, OK, that's probably the same point. And then after we match all these features, we can find the best alignment for the images. And then we can blend them smoothly together so that you don't see the separation between the images. So after this step, we have one single big image, which, for instance, for the painting I showed earlier, is about 500 megabytes. So at this point, there's still a step needed to put it on the web because we don't want users to have to download 500 megabytes just to see one painting. So what we do is that we slice it up in tiles. So we cut it in square tiles that are all 512 pixels by 512. And we also make smaller versions of the painting with fewer tiles, until at the top of the pyramid, you only have a single tile of thumbnail of the image. And so that way, when the user navigates the image, like pans around and zooms in, we only need to load the tiles that are needed to show the part of the painting that the user is looking at the current zoom level. So that's how capture works. So now I'm going to tell you a bit about a specific challenge I've been working on so that you know what I'm actually working on. So, and that challenge is looking for, the quest for sharp pixels. So trying to get the sharpest pictures we can. As I explained, we take hundreds of pictures of the painting, and most of the time they're sharp, but also sometimes we notice that we have some that are blurry, which is obviously bad because blurry pictures, I mean, we're not getting the best quality we could, and also then when we stitch them together, you can see the separation between the sharp picture and the blurry picture, so that doesn't look very good. And also, sometimes we actually fail to stitch because when we try to match the features between the images don't look like each other because one's sharp and one's blurry. So the idea was to try and detect automatically when we took a blurry picture so that we can immediately take another one. And trying to detect trying to evaluate the sharpness of a picture is quite a common problem. There's actually lots of research papers on it. So I read a bunch of papers, and I also looked around other Google projects to see what they were doing, because I'm not the first one to try and determine if an image is blurry or not. And I gathered a data set of some of our sharp pictures and some of our blurry pictures, and I tried these algorithms on them. And actually, none of them work very well on my data sets. And there are several reasons. One reason is I think most of these algorithms work better on autofocus blur. So basically, there are two reasons why you can get blurred. One is because your object is autofocus, so your camera is focused in front or in the back of your object. And the other is motion blur, because you move the camera while you are taking the picture. And actually, it seems that most of the blur we get is from motion blur. So, I mean, the camera is not moving, but actually, we're taking pictures that are so zoomed in that even like the tiniest shake of the camera causes blur. And and that's a kind of blur that's a bit harder to detect. And another thing that makes it a bit more complicated is the fact that we have some pictures that look like this. So, you know, when we are capturing a drawing, and there's like the drawing in the middle, and on the side is just paper, we have pictures that look like paper. And most algorithms will say, oh, that's pretty blurry. But actually, it's a sharp picture of a piece of blank paper. And even for me, when I was gathering my data set and trying to find sharp pictures and blurry pictures, sometimes it was hard for me to tell if they were sharp or not. So if it's hard for me, you can tell it's going to be tricky for an algorithm. So at that point, I was a bit disappointed that it didn't work. And then my colleagues came to my rescue and like gave me a million suggestions, you know, like more possibilities than combinations of my Rubik's cubes. And I was like, I can't test all of this. I mean, I could spend months trying to, I'm sure this is a problem that can be solved. I could spend months trying to solve it. But actually, at that point, I thought that a better approach would be to try and prevent the shaking or the blur from happening in the first place. So why are we getting blurry pictures? I said it's because of shaking. So how do you get rid of shaking? Typically, a photograph will tell you, well, you use a tripod. So we already have a very sturdy tripod. It's very big and heavy. But the fact that we take pictures that are so zoomed in means like really, when it's shaking a tiny bit, and you can't even see, like I look at it and I'm like, it's not shaking, but actually it is, when you look at the camera view, it is shaking a bit, and so we are getting blurry pictures despite this very heavy industrial tripod. So what we can do is try and use an accelerometer to detect when the camera is moving. And we actually already have an accelerometer on the camera. I didn't add it, it was already there on that custom board that I mentioned. And we have an algorithm that's supposed to detect shaking and prevent taking pictures when it's shaking. So if we already have this, why am I getting blurry pictures? So I mean, that was the question that I asked myself. And obviously, the shaking detection algorithm was not working very well because we got blurry pictures even though it said it's fine. And also sometimes, when we were in museums, the shaking detection algorithm was saying all the time, oh my God, it's shaking, I can't take a picture, even though everything seemed fine. And when I had to SSH in Colombia, that story I mentioned earlier, that was because of a shaking problem. It kept saying it was shaking, so the operator could not capture, even though everything seemed fine. So I didn't know anything about accelerometers or signal processing or anything. And you know, as I said, there was nobody on the team who knew anything about this. So I dug up the schematics of the power board and the data sheet of the accelerometer, and I spent hours trying to understand what the firmware was trying to do. And then finally, I wrote some tools to record some data. So on the left, I recorded the camera images so that I could see visually if it looked like it was shaking. And on the right, you have the accelerometer data. So there's 3 lines for X, Y, and Z axis. And so after looking at this data, what I realized is that probably we were giving too much importance to high frequencies and not enough to low frequencies. And so I try and modify the algorithm to have a low-pass filter to remove the very high frequencies, which are just noise, which are not actually causing blur, and so that we can detect the lower frequencies, which actually cause blur. And so that's not actually really the end of the story, because I'm still working on this. I haven't deployed the new version yet, because that's the fun thing with hardware. I said you have to test it a lot. I have to test it on different cameras, because maybe they vibrate at different frequencies and in different conditions. Because well, maybe here at my desk it's fine. Maybe in Colombia it's not fine. Well, maybe I won't go to test it to Colombia, but you need a lot more testing. So. To summarize, working on this project, it's fun and challenging, and sometimes it's also frustrating, but at the same time, it's also very rewarding, because at the end of all this hard work, we have several thousand pictures of very high-resolution pictures of paintings that we've captured and that we have available on the web at google.com/cultural institute, so you can go check them out over there. And sometimes you also get very nice messages from users, so that's really gratifying, and that really makes it worth the effort. Thank you. Questions? Questions?
Hi.
Hello.
Hello. I saw that it's a camera inside, so I guess it has brand. And did you happen to work with the brand of this camera to, all this algorithm and I don't know, to improve this camera, or with the company that built this camera?
So the actual DSLR camera that's inside is an off-the-shelf camera, so it's a normal camera that you can buy. It's a Canon camera. It's a 7D Mark II, if you know anything about photography. I didn't know anything about photography before joining this project, by the way. I learned some stuff now. Now I know some stuff. We also have a professional photographer that helps us and that goes to museums sometimes, so that also helps. But yeah, it's a normal camera, and I think this model is working pretty well for us right now. I'm not sure if that was exactly your question.
My question was basically, did you think about to work with a camera company that built this Canon, or with Canon? I don't know, because I guess they have more experience about building cameras. So.
Yeah, I guess that's a good question. So I think we're happy with the camera itself, and the value we're adding is not the way we're getting very high resolution images is not by having the best camera in the world that has the most pixels in the world. Is by just having a normal camera and taking lots of pictures and then stitching them all together. And we also want it to be a normal camera because we don't want this to be too expensive. We don't want it to be low cost and efficient.
Okay. Thank you. Yeah, it's.
There's no question over here.
Hi.
Hi.
So what is your technique to stitch correctly the different image that you are taking?
So I tried to explain that quickly at one point. So you might think that we can, so we know where we took the images, right? Because we know where the camera was pointing at, and you'd think we could just use that information, but actually it's not precise enough. So the way we do it is by, sorry, I'm gonna put this down, is by actually looking at the pixels of the images and trying to, so we take images that overlap a little. So we have each area is on several images, and then we check for these overlaps, and we figure out how what's the best alignment for the images and how best to stitch them. I hope that makes it a bit clearer. I'm not sure if that's the case.
So can you tell us how many pictures on average do you take for each artwork? And do you have a paper explaining the algorithm of, the stitching part and before the...
I don't know the average number. I think it's probably on average between 500 and 1,000. We don't have a paper or anything explaining it. If you guys want to learn more about it, you can email me. My address is Marla, my first name, @google.com. Because I don't really have time right now to explain everything in detail. Also, I don't know the most about it. The one who knows the most about it is my colleague, the other engineer who works on it. But really, it's a bunch of existing techniques, like looking for features. There are algorithms that exist to look for features. Matching features is just features are described by vectors. We just look for the Euclidean distance of the vectors and things like that. But really, no, we don't use machine learning. Not that I know, but maybe, you know. I think I'm out of time.
The final question.
Sure.
Did you finish that Rubik's Cube as you were standing up on stage?